Okay. So very good afternoon to one and all. Happy to see many of you here. Good afternoon, Srinidhi. Good afternoon, everyone. Very good afternoon to all of you. Okay. So let's go ahead. So today we are going to start with a new chapter called General Organic Chemistry. Okay. Which is abbreviated as GOC. So this is the very first lesson of the separate branch of chemistry called organic chemistry, right? So we have three branches of chemistry, right? So one is physical chemistry and the other one is inorganic chemistry and the other one is organic chemistry. So this is the third branch of chemistry called organic chemistry, and this is the very first lesson of your exam, okay, in class 11. Got it? So let's go into the introduction to organic compounds. So organic compounds are vital for sustaining life on Earth. Okay. If a life has to sustain on Earth, then organic compounds are playing a major role. For example, if you take DNA, which is called as deoxyribonucleic acid, it contains the base pairs, right? It contains base pairs. So the one of them is adenine and the second one is thymine, cytosine and guanine. So these are the base pairs which pair themselves. AT and GC, right? A will adenine will pair with thymine and cytosine will pair with guanine, and they will form this DNA structure. So in these four base pairs, if you see, we have the organic compound present in it, right? Nitrogen, hydrogen, oxygen. So they are making an organic compound and they are joining together and forming this DNA. Okay, so this is a very important compound which are vital for sustaining the life on Earth. Okay, not only this, it has been used in fuels also. Fuels means if you take petrol, okay, if you take petrol is a liquid, right? Petrol is a liquid. The physical state of the petrol is liquid. And that is a chemical compound which is made up of hydrogen and carbon. Which is made up of hydrogen and carbon. Okay, so here in this compound we have 8 carbon. So 8 carbon containing hydrocarbon is called as octane. It is called as octane. Okay, clear? So octane is the compound. It is an organic compound which is present inside the fuel called petrol. Okay, and also we are using this organic compounds in polymers. For example, if you take polyvinyl chloride, the PVC pipes, okay? So a PVC means polyvinyl component. Polyvinyl chloride is is an organic compound. Okay, it is an organic compound. So the formula is C2H3Cl N times. Okay, polyvinyl chloride. Okay, it is used as a polymer and also in the dyes. So organic compounds are present in dyes also. So this is a crystal violet dye and the structure of the compound is like this. Okay, it has a three aromatic ring and some amine groups, nitrogen groups are attached to it. Okay, so it is a crystal violet structure, which is an organic compound. Okay, so not only in dyes, it is also present in medicines. The very common example for a drug which I can take is aspirin. Okay, so aspirin is used to treat the pain, etc. Right? This used to treat mainly the fever. So this is the structure of this aspirin. Okay, structure of the aspirin tablets, which is an organic compound. Is an organic compound. So like this, organic compounds are used in the day-to-day life in many aspects. Got it? So we have to study about those compounds, right? It is very important to study about the compounds that we use in our day-to-day life. Got it? So let's go into deep about these compounds. So next we are going to discuss the synthesis of organic compounds. So initially, a person, a scientist called Jacob Berzelius. A person called Jacob Berzelius proposed that vital force was responsible for the formation of organic compound. Okay, he said that vital force was responsible for the formation of organic compound. Vital force means some other force, some supernatural kind of force. So that was responsible for the formation of organic compound. But later on, what happened? A scientist called Friedrich Wöhler. Okay, F. Wöhler. So this person synthesized an organic compound in his laboratory itself. And the name of the compound is urea. So he synthesized this organic compound urea from an inorganic compound ammonium cyanide. Okay, ammonium cyanide is an inorganic compound. And the formula for that is NH4CNO. NH4CNO, NH4 plus and CNO minus. So this is ammonium cyanide. It is an inorganic compound. It is an inorganic compound. Okay. He took this inorganic compound and heated this in his laboratory. And by heating, he got urea. The formula for urea is NH2CO NH2. Okay. So urea is an organic compound. Urea is an organic compound which we are finding in the cow dungs and all, right? So it is an organic compound. So since Euler discovered or synthesized the organic compound from an inorganic compound in the laboratory itself, he was against the previous person, Berzelius concept. Okay, so Euler said that vital force is not responsible. I can also prepare the organic compound in the laboratory from the inorganic compounds. So he was arguing with that thing, and he said many things, and later on many people have come up, and one among them is Kolb's, Hermann Kolb. Okay, Hermann Kolb came and he synthesized an organic compound called acetic acid. Okay, CH3COOH is an acetic acid, and he synthesized acetic acid in his laboratory. And after Kolb, Berthelot have come, Marcelin Berthelot. He synthesized CH4. What it is? Methane. Okay. So it is methane. All these compounds, urea, acetic acid, methane, all these organic compounds were synthesized from inorganic sources only. Okay. All the organic compounds were synthesized using inorganic sources in the laboratory. Okay. So in all these three compounds, if you observe all these three compounds very carefully, all of them are made up of carbon, right? All of them are made up of carbon. If you take methane, it has carbon. If you take acetic acid, its formula is also CH3COOH. Okay. And Friedrich Wöhler also discovered a compound called urea that also has carbon inside it. So why carbon? So organic compounds mainly contains carbon. Why? Can anyone give me the reason for this? Can anyone give me the reason for this? So why carbon is playing a major role in forming the organic compounds? So we have 118 elements in the periodic table, right? But in the branch of chemistry called organic chemistry, we are mainly studying about the carbon. Very good, Pragati. Your answer is the correct answer. Exactly correct. Suhra, great. So it is because of these two reasons. One is catenation. Very good, students. Taushia, Ajmala. Exactly correct. Catenation and tetravalency. Because of these two reasons only, so carbon is able to form n number of organic molecules. N number of millions and billions of organic compounds are formed by carbon. Okay. So not only these two. Okay. So these are the main points, main reason. But we are going to study in detail about this carbon. Okay. Like we are going to study the introduction and the representation, classification, and the nomenclature of these compounds. Okay. So let us try to cover these topics in today's session. Okay, let me enter into the introduction to organic chemistry. So far I have discussed the introduction to organic compounds in the daily life. Now we'll enter into the introduction to organic chemistry. So as you guys have said, organic compounds are numerous in number. Okay, numerous. Numerous means many. Organic compounds are numerous in number due to the two reasons. One is due to the high catenation carbon ability, and the second reason is carbon tetravalency. Okay, so these are the reasons. Now, coming to the definition of these two terms. What is meant by catenation? Can anyone tell me what is meant by catenation? Already you have studied the definition of catenation in your class 10, right? So can you guys try? Nandini? Yeah, it is self-linking property of a carbon. It can form long chains. Okay. Ability of carbon to form long chains. Correct. All of your answers are exactly correct. Exactly correct. So catenation is the ability of carbon atom to form long chains or rings. Ability of carbon atom to form long chains or rings is known as catenation. Okay, carbon has that ability. Okay, carbon has that ability. The element with highest catenation ability is carbon. So ability to form long chain means one carbon can form bond with the other carbon. Okay. So second carbon can form bond with other carbon. So the self-linking property we can say. So it can form a long chain of compound, or one carbon can bond with other carbon in a cyclic manner, and they can form a ring also. Ability to form a ring. So this property is called as catenation, and it is very high for carbon. Okay, very first reason is this. Then the second is tetravalency. So what is tetravalency? The ability to form. Yeah, very good, Bindu. Taushia, good, good. Harmit, all of you are doing great. So the ability of carbon atom to form 4 bonds. So why 4 bonds? Because the valence electron for carbon is 4, right? Valence electron, the valency of carbon is 4. Valency of carbon is 4, so it can form only 4 bonds, not more than that. Yeah. So the ability of carbon atom to form 4 bonds tetravalency. Okay. So to exhibit this tetravalency, carbon forms all 4 single bond. All 4 single bond. 4 single bond means like this. Okay. 2 double bond. 2 double bond means one carbon. Here one double bond and here another double bond. So totally 4 bonds around one carbon. One double bond and 2 single bond. One double bond and 2 single bonds. So this is another type. And one triple bond and one single bond. One triple bond and one single bond. So in all these 4 cases, if you see around the carbon, we have 4 bonds. Okay, so those 4 be formed in either one of these fashion. Got it? So this is the explanation about catenation and tetravalency. Taushia, isomerism is a separate topic. Okay, it is not the property of carbon. It is a separate topic which we will discuss in the upcoming classes. Okay, isomerism means the compounds having same formula, same molecular formula, but different structures. Those are called as isomerism. So we will discuss the types of isomerism and the subcategories of each isomerism and the examples. Those things I will tell you in the upcoming classes. So it is one of the topic under this lesson. It is not the property of carbon. So in isomerism, we will study about the organic compounds only, right? So organic compounds are made up of carbon, no? So we will discuss about the compounds of carbon only there. But it is not the property. Okay. Fine. So do you guys have any doubt from the thing that we have discussed so far? We did not discuss much, but we have discussed about catenation and tetravalency, right? Are you all clear with it? Any doubt? Okay. Thank you, Devananda. Okay, students. So now, let me go for one tabular column. One tabular column. So that the table which I am going to discuss with you right now is very, very important. Okay. So I'm going to give a table for you. In the first column, I'm going to take the serial number, and second column is about the hydrocarbon, third hybridization, carbon-carbon bond length, example, and shape and bond angle. Okay. So the very first hydrocarbon is called as alkane. Okay, there are three types of hydrocarbon. Okay, we have a separate lesson called hydrocarbon in class 11. Once we complete this lesson, we can move on to that. So in that lesson, we will talk about the types of these hydrocarbons only. Okay, the very first is called as alkane. The hybridization of carbon in alkane is sp3. Ajmala, very good. Alkane, alkene, and alkyne. Very good. So the hybridization of alkane is sp3. Okay. So carbon-carbon bond length will be 1.54 angstrom. Example I will come to you at the last. Shape of the system, shape of the molecule will be tetrahedral, and the tetrahedral bond angle is 109 degree, 28 minutes. Okay. Pragati, Taushia, good, correct. Then coming to alkene, the hybridization is sp2. Hybridization is sp2. Ishrat? Correct, correct. I will come to the examples at last, okay? sp2. And the carbon-carbon bond length in case of alkene is 1.34 angstrom. Okay, and the shape is trigonal planar with 120 degree angle. And the third hydrocarbon is alkyne. Okay, alkyne. Alkyne. Hybridization is sp. Hybridization is sp, and the bond length is 1.20 angstrom. And the shape is linear. Bond angle is 180 degree. So as you guys have said, the very simplest example for a alkane is methane. Okay. And for alkene, ethene. Okay. C2H4. And for alkyne, C2H2, ethine. Okay. Very good. Very good, Ishrat. Ethene and ethine. So this is methane. Methane means one carbon containing hydrocarbon. I can go for ethane also. Ethane means I will have 2 carbon which is attached with 6 hydrogen. Which is attached with 6 hydrogen. So this carbon-carbon bond length is 1.54 angstrom. Clear? The sp3 hybridization means the carbon will have only single bond around it. And sp2 hybridization means the carbon will have double bond around it. sp means carbon will have triple bond around it. Got it? So this is ethane. This molecule is called as ethane. And C2H4 is called as ethene. And the last compound is called as ethine. Okay? So the bond length, bond angle, and the shape. All these are very important. So tetrahedral. Tetrahedral means 4 faces. Okay, if you go for methane, so methane has 4 faces. So this is the front face and this is left face. This is your right face and bottom face. There are 4 faces. That's why it is called as tetrahedral. And this tetrahedral bond angle is very, very important. You can go for 109 degree, 28 minutes, or it is 109.5 degree. Okay, 109.5 degree. Both of them are correct answer only. Okay. Then for alkene, it is trigonal planar. If you take one carbon, the geometry around that particular carbon is trigonal planar. It is a triangle kind of thing. Okay, so that's why the bond angle is 120 degree. And if you go for ethine, it is in a straight chain manner, right? So it is linear and the bond angle around the carbon is 180 degree. Okay, bond angle, shape, carbon-carbon bond length, and the hybridization example, everything is important. Okay, so you guys should not make any mistake if any question is asked based on this tabular column. Okay, so do you guys have any doubt? Everything is clear for all of you? Okay. Okay, that's great. Harmid, C2H8. C2H, such kind of molecule is not existed. C2H8. We don't have any molecule with the formula C2H8, my dear. It is C2H6. Are you asking about C2H6? Yeah, two tetrahedrons are connected only. So I will show you. I will show you. Just listen. I will draw and show you. So C2H6. C2H6, right? 6 hydrogens are here. So the hybridization of both the carbon is tetrahedral. So around this carbon, around the first carbon, if I try to connect, I will get a tetrahedral like this, right? This is one tetrahedral. And if you connect the atoms which are attached with the second carbon, you'll get another tetrahedral. So two tetrahedrals will be like this. Clear? Clear? Shall I go for the next slide? Okay. All right. Okay, my dear students. So now I'm going to give you one question. Okay, you guys are going to find the answer. Write the state of hybridization of carbon in the following compounds and shapes of each molecule. So you are going to find out two things. I'm going to give you the compound. You are going to find out the hybridization and the shapes of each molecule. Okay, so you all know how to find out the hybridization, right? So if a carbon is having only single bond, sp3, double bond means sp2, triple bond means sp. Okay, and according to the hybridization, you can find out the shape also. So the very first molecule is CH2 double bond O. CH2 double bond O. Second molecule is CH3F. Third molecule is HCN. So can you go ahead? Can you go ahead with the answer for the first molecule? Give both the answer, hybridization and shape for compound A in your single message. sp2 is the hybridization, very good. What about the shape? sp2 is tetrahedral? No, sp2 is not tetrahedral, Taushia. Yeah, sp2 trigonal planar. sp2 means it is trigonal planar. Okay. So A is having sp2 hybridized carbon. So with the trigonal, I will draw the structure and show you. Listen. C double bond O. Here one hydrogen and here another hydrogen. Okay, carbon is having double bond, so it is sp2 hybridized and it is trigonal planar in shape. Got it? What about the second molecule, CH3F? sp3 with tetrahedral. That is exactly correct. sp3 with tetrahedral. So carbon is here. There are 4 bonds around it. So one is fluorine, the other 3 are hydrogen. Okay, so it is forming a tetrahedral structure with sp3 hybridization. Okay. Third one is sp linear. sp linear. Yes, it is sp and linear. So H, C, triple bond, N. Correct. sp with linear structure. Okay. So very good. All of you have done a great job. So I hope the introduction to organic chemistry topic is clear to all of you. So here we have discussed how to find out the hybridization and how to find out the shape of the molecule. Okay. So now let me enter into the second topic of this lesson, which is called as representation of organic compounds. So how will you represent the organic compound? How to represent the organic compound? So structural representation of an organic compound. So one particular compound can be represented using a complete structural formula, or it can be represented using a condensed structural formula, or it can be represented using a bond line structural formula. Okay. So these are the three ways in which we can represent an organic molecule. Okay. According to its formula. So let us discuss one by one. So how to represent using this complete structural formula, or what is complete structural formula? Let me take examples for this. Okay. Let me take ethane as an example. So here if you see, we have 2 carbon and 6 hydrogens, right? So all the carbon bond and carbon hydrogen bonds are represented in this structure. Okay. So if all the bonds present in the molecule are represented, or if it is shown in, it is called as a complete structural formula. Yeah, using dashes. Those are not called as the dashes exactly. They are actually bonds. Okay. They are completely expressed using their bonds. So they are called as complete structural formula. So one more example, if I want to give, I can go for ethene. Ethene has carbon-carbon double bond and 4 carbon hydrogen single bond. If I go for ethyne, 1 carbon-carbon triple bond and 2 carbon hydrogen single bond. Okay. So if I go for methanol, so this compound is called as methanol. CH3OH is called as methanol. So I can represent the 3 carbon hydrogen bond and 1 carbon oxygen bond and 1 carbon hydrogen bond in this manner. Okay. So here all the bonds between the 2 atoms are represented, which are called as complete structural formula. All right. So the difference between these two molecules is, so oxygen has 2 lone pairs, right? So the lone pairs are denoted here, and here we don't have the lone pairs. Both of them are correct. Both of them are complete structural formula. All right. So this is one. The second classification is condensed structural formula. If I take the same ethane molecule, so this is the ethane molecule, right? So if I write this molecule in the form of CH3, CH3, then it is the condensed structure. So what I have done here, I have removed all the carbon-carbon bonds and carbon-hydrogen bonds. Okay, CH3, CH3, just the formula I have written. So it is the condensed structural formula for ethane. Okay, if you go for ethene, what is the structural formula? CH2 double bond CH2. So here for double bond and triple bond, you should represent. Okay, you should mention the double distance. So the first student, just give me a second. Just give me a second. Yeah. Can you all able to see the screen now? Can you all able to see the screen? Can you all able to see the screen? Yes, okay. So there were some issues in the Zoom. That's right. All right. Fine. So let me go into some more thing about the condensed structural formula for octane. So we have discussed about the octane in the beginning of the lesson, right? So petrol contains octane, and I have said that there are 8 carbons. That there are 8 carbons in octane molecule. And if all the carbon-carbon and carbon-hydrogen bonds are removed, I will have to write the structure like this. And this is the condensed structure of octane. And I can further condense this structure. I can further condense this structure and I can write like this. So there are 6 CH2. 1, 2, 3, 4, 5, and 6. There are 6 CH2. So I can write the structure like this. CH3, CH2 6 times and CH3. Okay, so this is the further condensed form of octane. All right. So do you have any doubts in complete structural formula and condensed structural formula? Shall we go for the bond line structural formula? Yes. Okay. Great. So coming to the bond line. So here what we have to do, carbon and hydrogen are not shown. Here in bond line structural formula, carbon and hydrogen are not shown. Okay, the C and hydrogen you cannot see in the formula. And the lines representing the carbon-carbon bonds are drawn in the zigzag fashion. For example, let me take 3-methyl octane. So 3-methyl octane is an organic compound and it can be represented in many forms. So one among the forms is this. Okay, 3-methyl octane. So I will tell you how to find out the name from the structure, and also I will teach you how to find out the structure from the name. Okay, so those things will be discussed in the IUPAC nomenclature part of this lesson. Okay, don't have to worry. So I have 1, 2, 3, 4, 5, 6, 7, 8 carbons, right? And to the third carbon, I have a methyl group. So that's why it is called as 3-methyl octane. I will discuss about the nomenclature later. Okay. So 3-methyl octane can be represented like this, or it can be represented like this also. What is the difference between these two structures? In the second structure, carbon-carbon bonds are shown, but in the first structure, everything is omitted. Okay. And also it can be represented like this, in the third form like this. So what is the difference between A, B, and C? So in case of C, no hydrogen and no carbon is shown. Okay. Only the lines are denoted, carbon-carbon bonds are drawn in a zigzag fashion. Okay. So we should understand that each edge denotes the carbon. Each edge denotes the carbon. So there are 8 carbons here, and to the third carbon, the methyl group is attached. Methyl group is attached. All the terminal carbons are called as methyl group containing carbon. C means CH3. So here also it is CH. And here also it is CH3. Okay, and if you go for the in-between carbon, if I go for this carbon number 2, this carbon has only 2 bonds. So the remaining 2 are hydrogen. The remaining 2 are hydrogen. Valency of carbon is 4, right? So it should be 2 hydrogen. And if you go for third carbon has 3 bonds. So only 1 is hydrogen. If I go for the fourth carbon, this carbon has 2 bonds. So the remaining 2 are hydrogen. So for fifth carbon also it is CH2. Sixth carbon also CH2. Seventh carbon also CH2. Okay, so this is what we are writing like this. Clear for all of you? So according to the valency of carbon, look the number of bonds around carbon and satisfy the valency by putting the hydrogen. All right. Do you have any doubt in drawing the bond line structure? It is very easy. If you're going for the bond line structure, you can just go for drawing the lines and you can get the answer immediately. But if you go for the condensed or complete structure, every time you have to put CH3, CH2, CH2 and all. So it is a time consuming thing, no? So better learn how to draw the bond line structure for all the molecules. It is very easy and it is very understandable if you practice. Organic chemistry is the branch of chemistry where you need practice. Okay, nothing much to memorize, but practice is very important. Every day you have to practice with some compounds. Every day you have to study That is what I used to tell as consistency. So consistency is very important. Consistency is very important. Consistency means every day you have to study. Got it? Continuously you have to study. So those things are very important to get good marks in organic chemistry. So you don't have to solve any problem. You don't have to memorize and think of those things. Nothing is needed. Okay, conceptual understanding alone is very important to get good marks in organic chemistry within few minutes or few seconds. Okay. Ajmala, you want to know my name? My name is Anandi. Andh. Varalakshmi, don't worry. Once I complete some part of this lesson, I will solve the questions from JEE and NEET also. Okay, sometimes we used to solve the JEE questions and NEET questions in between the chapters, and sometimes I go for the questions at the end also. Okay, but for organic chemistry, I have to take the questions and solve once I complete each topic so that you can understand it better and you will apply. Okay. Yeah. Sanket, you have raised your hand, it seems. Do you have any doubt? Suhra, thank you so much. Thank you so much. Your name is also a nice name. Okay, Sanket. So Harmit is asking that can methane be represented in bond line structure? No, my dear. Only if you have more than two carbon. Only if you have more than two carbon in your compound, you can represent it in bond line structure. Methane cannot be represented in bond line structure. Okay. We have only one carbon, right? So one carbon containing that alkane cannot be represented in methane, but all other structures can be represented using a bond line structure except methane. Okay. We need 2 points to draw a line, right? Point A and point B. If you draw these 2 points, the edges are nothing but carbons. No, we need at least 2 carbon to denote the formula with the bond line structural formula. Okay. Yeah, it will be a dot if you represent, but you cannot represent using dot. This name itself says that it is a bond line, right? Bond line. Okay. Shall I go for the next? So here you see, as I have already told, all the terminals represent the methyl group. Methyl group means it is CH. Clear? Let's go for the next. Let's go for the next. One more thing you need to keep in mind regarding this bond line structural formula. Okay? The thing is, the only atoms specifically written are oxygen, chlorine, and nitrogen. So in the bond line structural formula, we are not representing the carbons or hydrogens. But we have to represent the other atoms. Oxygen, chlorine, and nitrogen will also be the part of your organic compound. Okay, in some compounds, we will have oxygen, chlorine, nitrogen, sulfur, phosphorus. Many atoms will take part in the organic compound. Okay, except carbon and hydrogen, all other heteroatoms. Heteroatom means other different atoms. So they has to be denoted. For example, I will take 2-bromobutane. 2-bromobutane can be represented in various forms. 2-bromobutane formula can be represented like this, or it can be represented in the second way like this, or it can be represented like this. Okay. So this is these two are the condensed formula where only the carbon-carbon bonds are shown. This is carbon number 1, 2, 3, 4. So to the second carbon, I have bromine. But in the third structure, you see, carbon and hydrogens are not shown, but the bromine is shown. Bromine is written. Okay. So like this, if you have other atoms than hydrogen and carbon, you have to write the elemental form of that compound. Okay, element in the compound. So don't forget to mention the symbol of oxygen or chlorine or nitrogen while writing the bond line structure. Clear? Shall we go for one more thing? Let me discuss about the cyclic compounds. So bond line structural formula for cyclic compounds. So far we have discussed the straight chain compounds and branches. So let me go for cyclic compounds. So this is a cyclic compound. Okay. So 3 carbons are arranged in a cyclic manner. So since there are 3 carbons, it is called a cyclopropane. Okay. And if you remove the carbon and hydrogen, how will you denote it? Like a triangle. But it is not a triangle in chemistry, right? It is cyclopropane in chemistry. It is triangle in mathematics. Then what about this? 5 carbons arranged in a cyclic manner. Cyclopentane. So I have to draw this like a pentagon. Okay. And if I go for 6 carbon containing cycle, I have to write like a, draw like a cyclohexagon. Okay, it is a hexagon kind of thing. So this is how you have to denote the cyclic compounds using bond line structural formula. Okay. So if there are any heteroatom attached, suppose if I have chlorine here, what I have to do? I have to draw the cycle like this and I have to denote the chlorine. Okay, I have to mention this chlorine in the cycle. Okay, you cannot leave chlorine as such. You have to mention because it is a heteroatom. All right. So any doubt from the structural representation of an organic compound? Are you all clear? Shall I go for the 3-dimensional representation of an organic compound? Shall we go for it? Okay. Okay, great. So let's go into the 3-dimensional representation of organic molecule. So the 3-dimensional structure of organic molecules can be represented on paper by using certain convention. So the paper or the board which we are using to write is a 2-dimensional plane, right? So in a 2-dimensional plane, if you want to denote a 3-dimensional structure, you have to follow some conventions. Okay? Listen, I have taken a compound, methane. So this is a methane. Methane has 4 carbon-hydrogen bonds. It has 3 different types of bonds, right? So one is a normal line. So these two are looking like a normal line, right? So these two denotes the bonds in the plane of paper. Okay, if you are seeing the class in your tab or if you are seeing your class in your class in your LED screen, so that LED screen or the laptop or the tab which you are using is a plane. Okay, so XY plane. So these two bonds are there on the plane. And we have on dashed wedge, right? Dashed wedge. It is also a bond denoted in a dashed wedge kind of manner. So this means that the particular atom, this hydrogen atom is away from the observer. Away from the observer means this hydrogen atom is below the plane. It is below the plane, below the tab, below the laptop, below the computer. Okay. And the last one, this is called a solid wedge. It is towards the observer. Towards the observer means above the plane. Above the plane. Got it? So the 2 bonds are on the plane. One is below the plane and the other one is above the plane. Below dashed wedge, above the plane means solid wedge. Okay, all these 4 are the bonds of hydrogen with carbon. So this is how you have to denote the 3-dimensional structure of organic molecules in a 2-dimensional plane. Okay, clear? So mostly the sp3 hybridized system only will have this 3-dimensional structure. sp2 is trigonal planar. It needs only xy plane. And if you go for sp also, it is linear, right? So it also requires xy, 2 plane is enough. Okay, only for sp3 hybridized system, we need the. All right. Shall we go for the next topic? Shall we go for the classification of organic compounds? Do you have any doubts in the introduction to organic chemistry and in the structural representation of organic molecules? Do you have any doubts in these two topics? No. Okay. So let's go for the classification. Organic compounds are classified into two. So mainly it is classified into two. So first classification is acyclic compounds, open chain compounds. Acyclic compounds are open chain compounds. For example, CH3, CH3. Okay. Or CH3, CH2, CH2, CH3. Okay. Anything. Any compounds which are of open type, it is called as acyclic compounds or open chain compounds. The second classification is cyclic or closed chain compounds. Cyclic or closed chain compounds or ring compounds. Okay. Under this cyclic, I have some classification. The first one is homocyclic or carbocyclic. And the second classification is heterocyclic compounds. Cyclic is again classified into two, homocyclic and heterocyclic. Homo, what is meant by homo? Homo means same. Homo means same. If all the atoms which is forming a cycle are same, then it is called as homocycle. For example, we have seen cyclopropane, cyclopentane, cyclohexane examples, right? So those are the examples of homocyclic compounds only. Okay, so here all the atoms which has formed this ring are carbon. So all the atoms are same. So it is called as homocyclic compound. Since all the atoms are carbon, it is also called as carbocyclic. It is also called as carbocyclic. Clear? Then coming to the second classification, hetero. Hetero means different. Hetero means different. If any one of the atom which is forming the ring is different, then it is called as heterocyclic. Okay, for example, this is a 5-membered ring, but 4 atoms are carbon and the last one is oxygen. So we have one different atom which is forming the ring. So it is an example for heterocyclic. Okay. But homocyclic is again getting classified into alicyclic and aromatic. Homocyclic is again getting classified into alicyclic and aromatic. Okay. Aromatic compounds are again classified into benzenoid and non-benzenoid compounds. Benzenoid and non-benzenoid compounds. Okay, so this is the classification of organic compounds. So do you have any doubt in this classification? So don't worry about this alicyclic, aromatic and all. I will give some examples under each type and I will discuss in the next slides. Okay, so don't think of what is alicyclic, what is aromatic. I will discuss everything in detail. Okay, so do you guys have any doubt till this? Do you guys have any doubt in this? No doubt? Okay, fine. So let me go for the first one, the first acyclic. So I will go for this classification. I will give you some more examples under this type. So acyclic compounds consist of straight or branched chain compounds. It consists of straight or branched chain compounds, which is also called as aliphatic compounds. Which is also called as aliphatic. Ethane, acetaldehyde, isobutane, acetic acid, all these will fall under this category. Okay. So all the 4 compounds has a straight chain or some branched chain thing. Okay. So all these will fall under this acyclic or open chain compound. Open chain compound. Closed chain compound means it is getting classified into homo and hetero, right? Homo means I have already told you, if all the atoms forming the ring are same, then it is called as homo. Okay, it contains carbon atoms joined in the form of a ring. Then for hetero, one will be different. So this compound is called as tetrahydrofuran. And if I am having sulfur, it is called as thiophene. So sometimes atoms other than carbon are also present in the ring, and those compounds are called as heterocyclic compounds. Okay. Then next I will give you the explanation for aromatic. Aromatic compound means benzene ring containing compound. Okay, benzene and other related ring containing compound. So what is benzene? The formula for benzene is C6H6 and the structure will look like this. Okay, this is the structure. So this is a benzene. So the aromatic compounds was again classified into two, benzenoid and non-benzenoid, right? So benzenoid compound means benzene ring containing compounds. Benzene ring means 6 carbon containing benzene ring containing compounds. So we may have some substitutions like this. So here I have NH2, but still it is a benzenoid compound. Here I have 2 benzene ring, so it is a benzenoid compound. Okay, if you have 6 carbon as a ring, then it is a benzenoid compound. Okay, non-benzenoid. Non-benzenoid examples are azulene and tropolone. So here in these two cases you see, so I have 2 rings here in azulene. 1, 2, 3, 4, 5, 6, 7. One is a 7 membered ring and the other one is 1, 2, 3, 4, 5. And the other one is 5 membered ring. But in benzene, how many carbons we are having? 6. So it is an aromatic compound. Azulene is an aromatic compound, but it doesn't have 6 carbon like benzene. So it is falling under non-benzenoid. Okay. And in tropolone also you see 1, 2, 3, 4, 5, 6, 7. Again, we have 7 membered ring, but it is an aromatic compound, but not a benzenoid. So it is a non-benzenoid compound. All right. Clear? So this is all about aromatic. So all the atoms which is forming the ring are carbon only. But if you have a ring with more than 6 carbon or less than 6 carbon, then it will fall under non-benzenoid category. Okay? Clear for all of you? Shall I go for the last classification, which is heterocyclic aromatic? So from the name itself, you can understand what is a heterocyclic aromatic, right? So it will be an aromatic compound, but one heteroatom will be present. So you may ask me, ma'am, what is meant by aromatic compound? How to find out whether the compound is aromatic or not? So there are some criteria which I will discuss with you at the end of the lesson. Okay, under the topic aromaticity, we will discuss those things. So don't worry. Okay, so this compound is aromatic. I am saying this compound is aromatic. So just keep in mind that furan is aromatic. Okay, but it is having one heteroatom. So it is called as heterocyclic aromatic. And thiophene is also an example for heterocyclic aromatic. Then other compound is pyridine. In pyridine, I have nitrogen. Okay, nitrogen is also an example for heterocyclic. Pyridine is also an example for heterocyclic aromatic. Okay, clear for all of you? So these compounds are again classified on the basis of functional group and on the basis of families of homologous group. Okay, so we will discuss those classification in the next class. Tomorrow we will discuss. Okay. Yes, Pragati. 4 and plus 2 pi electrons will be there and it will show planarity. So these are the criteria under aromaticity. So we will explain, we will discuss everything in detail in that topic. Okay. So it's good that you know the criteria for aromaticity now itself. That's great. Students, do you have any doubt from today's session? You guys have any doubt from today's session? No? Okay. So what we have discussed today? We have discussed the introduction, structural representation, and the classification. Okay. So we have classified the organic compounds into different categories. And tomorrow we will discuss about the classification based on functional group and homologous group. Okay. So all of you, please revise the today's session before you come for the next class tomorrow. Okay. So see you all with the next set of topics in the next session. Till then, take care. Bye-bye. I have launched a poll. So guys, Please give your answers for all the 5 questions given in the poll and then get ready for your next class. Thank you.